In concept B, we're going to be focusing on something called heats of reaction. You're going to need your chemistry reference tables to look at something called table I, so you can take those out as we get started. So energy in reactions, it can either be endothermic, meaning that it absorbs energy from its surroundings, these tend to feel cold, or exothermic, they release energy to the surroundings, and thus the surroundings increase in temperature and feel warm. The energy of a chemical reaction is usually measured in heat. Alright, the change reaction is also called a change in enthalpy, or delta H. This is the difference in enthalpy, that's why we put the delta out in front, the amount of heat content between comparing the products and the reactants. So this is our equation to calculate delta H. We look at the enthalpy of the products minus the enthalpy of the reactants. Alright, since H is heat content, thus, if the delta H is positive, meaning that the products have more energy than the reactants, then it's absorbed energy to be endothermic. If delta H is negative, then it's going to be considered exothermic. So endothermic, where we absorb energy, we can see that energy is written to the left of the arrow, meaning that it's absorbing it. The heat is absorbed from the environment surrounding, thus the temperature of their surroundings decrease. Now, the products have more energy than the reactants after, again, the reactants have absorbed this energy for the reaction to take place. The energy is stored in the chemical bonds of the products. Now, this is excess energy, so this causes the products to be chemically unstable and highly reactive. Exothermic is a little bit different. We have energy written on the right-hand side or the product side, so it gets released as a product. Because heat is being released into the environment, it causes the temperature of the surroundings to increase. Now, the products have less energy than the reactants, and because of that, since they have less energy stored in their chemical bonds, they're actually more stable than the reactants were. Right, so I've already pointed this out a little bit about how we're going to be writing these. And exothermic reactions can be shown in two ways. Either you will have the reaction, and delta H will be shown as a negative amount of heat, or it can be placed within the reaction itself and written on the right-hand side. So either it's written on the right-hand side, or we can show it as a negative amount. So negative energy means it's exothermic, so you write it on the right-hand side. You'll never actually transfer that sign into the equation itself. The negative is simply telling you that it's losing that energy as a product. All right. An exothermic reaction in one direction must be an endothermic the other way. So for an endothermic reaction, when we've reversed it, compared to the left-hand column on your note packet, delta H is now positive. Now the positive amount of energy means that it's going to be written now as a reactant. So we've seen how, again, the sign has flipped for this endothermic reaction, which was reversed from our exothermic reaction, and the side that the 566 kilojoules is on has also changed. Now, if I want to double how much carbon dioxide reacts, I'm going to then have twice as much energy. So I originally have 2 moles of CO2 that's absorbing 566 kilojoules. If I double my coefficient to 4, so I've multiplied 2 times 2, I also have to do the same thing to my energy. So we've talked about in a previous unit about whatever we do to one coefficient, we do to the rest of the remaining coefficients. We also have to follow through and complete that same multiplication or division to our energy amount. So table I, which you should have out in front of you, contains the changes in enthalpies for the dissociations, which are compounds breaking up into ions. We also have included combustion in table I, which is different reactions. We commonly think of things burning, and other chemical reactions that you'll see on table I. Now, all these changes in enthalpies are for 101 kilopascals and 298 Kelvin, and they have to have the same exact phases as you can see them on table I. Now, a couple things that I want to point out to you that you're going to see me doing, and you might want to jot these down in your notes, is number one, if the reaction is in the reverse order than the equation on table I, we're simply going to flip that positive or negative sign for delta H. Also, if the coefficients have been increased or decreased to compare to the equation on table I, I'm then going to have to increase or decrease the delta H value by the same multiple. All right, so here are a bunch of examples. I'm going to be pulling up just little snippets of table I, but you should really be looking at table I for yourself. So you're going to locate this N2 plus 2O2 yields 2NO2. So you're going to find the exact equation in this case, which I've put here on the screen. Now this matches exactly number 1. That means simply that I can transfer my delta H to the table. So positive 66.4 kilojoules per mole. The positive tells me that it is endothermic. Now for number 2, we have another one that we're going to find directly on table I. So N2 plus 3 hydrogens plus 2 ammonias. So it matches exactly, so I can simply transfer that amount to number 2. So negative 91.8 kilojoules per mole, so it's exothermic. Now, number 3, we actually have reverse number 2. So I'm now taking my 2 ammonia molecules and breaking them into nitrogen and hydrogen. Okay, the coefficients still match, it's just simply the reverse. That means then the only thing I'm going to change from table I is the sign out in front. So instead of being negative, it's now positive, and thus an endothermic reaction. So again, if I flip the equation from table I simply reverse the sign. Now for number 4, if you look carefully, the one that's closest to number 4 is this equation here. But you can see that I've taken where I've had all coefficients of 1s and doubled them to be all coefficients of 2. Since I've multiplied my coefficients by 2 here, that means I have to take my value for delta H, and I'm going to also multiply it by 2 to get an amount of negative 787. And thus, because I have a negative delta H, I have an exothermic reaction. All right, and then finally for number 5, the most closely matching equation is this one here. 2CO plus O2 gives me 2 carbon dioxides. Now, 2 things have happened here. You can see that I've reversed this equation. So I'm going from what was my original product to my original reactants. So I'm going to flip this sign, so negative is now going to become positive. And I've gone from having a coefficient of 2, 1, 2 to my 1, 1, and 1/2. So I've divided all of my coefficients by 2. So I'm going to have to make sure then that I take my positive amount of delta H divided by 2 because all my coefficients were divided by 2 to get positive 283 kilojoules per mole. My positive sign indicates I have an endothermic reaction. Alright, so we'll be continuing on with these heats of reactions tomorrow in class. You are all set.